Assalamualaikum everyone. Today let's learn about refraction of light. There are two subtopics, refraction at a plane surface and second one refraction at a spherical surface. Before we proceed, let's look at these four experiments. Do you think you can recreate this experiment and get the same results? Well, of course you can because it's light refraction. What is refraction of light? It is the changing of direction of a light ray and its speed of propagation as it passes from one medium into another. So there are two things that change. The first one is the direction of the light ray and second one the speed of propagation. So refraction can occur either at a plane or spherical surface. For the refraction at a plane surface, here we have the incident ray, refracted ray, angle of incident, angle of refraction, normal line, and also two types of medium. So these two medium we label as N1 and N2. N is the refractive index of a medium. So how do we know which one is N1 and which one is N2? Any medium that contains incident ray is N1. Any medium that contains refracted ray is N2. So for this figure, incident ray is in N1 while refracted ray is in N2. So given that N2 is greater than N1, or we can say that N2 is denser compared to N1. So what happens if the incident ray travels from less dense to a denser medium? So we can see that the refracted ray bends toward the normal line. Next, what if the incident ray travels from denser medium to a less dense medium? So we can see that the refracted ray will bend away from the normal line. So you can compare these two figures and you can identify what will happen to the refracted ray when it travels from a medium to another. Please take note that there will be angle of incidence and angle of refraction where we measure this angle start from the normal line. So please make sure to sketch the normal line which is always perpendicular or 90 degrees with the plane surface. And then remember that N1 is the medium contained incident ray, while N2 is the medium that contains the refracted ray. In other words, less dense medium we call as rarer medium, while more dense medium we call as denser medium. For the law of refraction, we have the incident ray, refracted ray and normal line all lie in the same plane. Second one, for two given media or we have two types of medium, we can apply Snell's law which is sin I over sin R equal to N2 over N1, or you can write as N1 sin I equal to N2 sin R. So I is the angle of incidence, R is the angle of refraction, N1 is the refractive index for medium 1, or we can say that N1 is the medium that contains the incident ray, N2 is the refractive index of medium 2 or the medium that contains the refracted ray. What is a refractive index of a medium? The symbol is N and it is measure the optical density of a given material. Each material will have different density. A material with higher refractive index is more denser compared to a material with lower refractive index. The lowest refractive index for a material is air or vacuum, which is N equal to 1. For any light ray that travels from vacuum or air into the medium is given by N equal to C over V. where c is the light speed in vacuum or air, equal to 3 times 10 to the power of 8 meter per second, and v is the light speed in the respective medium. How to use this equation? This equation will help us to calculate the refractive index of each medium. For example, let's try to calculate for the water. The speed of light in vacuum or air is 300,000 km per second, while the speed of light in water is 225,000 km per second. When we substitute into this equation, n equal to c over v, then we get 1.33. Thus, the refractive index n for the water is 1.33. Let's try for the other one. For the vacuum, so the speed of light in vacuum is 300,000 km per second, and divide with the speed of light in vacuum also, which is 300,000 km per second, then you get 1.0. When you calculate for the refractive index of air, you will also get 1.0. So for the air and vacuum, the value for the refractive index is 1.0. Remember that for refractive index, n has no unit because we can cancel out the units during the calculation. Now let's move to the next subtopic, refraction at a spherical surface. There are two types of spherical surface. The first one is convex surface and second one is concave surface. So look at the refraction at a convex surface first. Here we have two medium. The first one is this one and second one is this one. It can be seen that the object is situated in front of this convex surface. So I label the distance of this object from the spherical surface as u. And then, since this is a spherical surface, so there will be a center of curvature. So how do we know where is the center of curvature? Look at the shape of the sphere. So this is the spherical surface. If we make it into a sphere, so the center will be at this side. So label C right here. And the distance of center of curvature from the spherical surface, you can label as R or radius. Next, there will be incident ray that will travel from the object and pass through the denser medium. So here we can draw the normal line from point C. And then what will happen if the incident ray travels from less dense medium to a denser medium? The refracted ray will bend towards the normal line. So the image will form at that side. And we can label the image distance V from the image to the center of the spherical surface. Next, let's look at the refraction at a concave surface. This is the object. And then label the center of curvature. So center of curvature is at this side because the spherical surface is like this. So if we make it as a sphere, so the center will be at this side. Then you can label the position of R, radius of this spherical surface, from the center to point P. Next, the incident ray will come from the object and then sketch the normal line straight from point C. And the refracted ray, since the incident ray travels from less dense to a denser medium, so the incident ray will bend towards the normal line. From this refracted ray, you can draw it straight until the image forms here. So we can see that this is the object distance and this is the image distance. Please take note that this is the refraction at a spherical surface, not on a spherical mirror or a lens, but spherical surface. So from these two cases, it will derive an equation which we call as spherical refracting surface equation. N1 over U plus N2 over V equal to, in bracket, N2 minus N1 divided with R. N1 is the refractive index of medium 1 or medium that contain the incident ray. N2 is the refractive index of medium 2 or medium that contain the refracted ray. U is the object distance from the center of the surface. V is the image distance from the center of the surface, and R is the radius of the spherical surface. So R depends on the position of C. So to determine the R, look at where is the point of C. To apply for this equation, you need to consider the sign convention. So please be careful how to understand about the sign convention. So look at the object distance. If the object is placed in front of the spherical surface, so this is a real object, so the sign is positive. If the object is placed at the back of the spherical surface, it is a virtual object, it's negative. While for the image distance, if the image form opposite side with the object, so it will be a real image. And if the image forms same side with the object, so it's a virtual image, negative. For the radius, if the point C situated in a medium of higher refractive index, it will be positive. If point C situated in a medium of lower refractive index, it will be negative. So let me show you the example. Let's say I have a convex surface right here, and the object situated here. If the object situated here, thus the incident ray will come from here. So this will be the N1 and this is N2. Then we'll have the incident ray, and I label the point C. This is the normal line. Refracted ray will bend towards the normal lines. So this will be the refracted ray. Image will form here. Let's look at the position of U, V and R. First, this is the U. So U is situated in front of the spherical surface. So U is positive. And image, this is the position of image. So V will be here. Since the image is from opposite side with the object, so this is a real image. So V will be positive. Don't confuse with the mirror. Okay, so for these cases, if the image form opposite side with the object, it will be a real image and the sign is positive. For radius R, so we know that R radius is being measured from the center of curvature to the surface. This is R. But how do we know that R is positive or negative? Look at the refractive index N. If the point C situated in a denser medium, so the R will be positive. Next example, I use a concave surface. Let's say the object is situated here. So this will be the U. U will be positive because the object is situated in front of the spherical surface. And then let's say the point C is here. So this will be the R. Since the object is situated here on this side, so this will be the N1 because the incident ray will come from the object. And this one will be N2. After the refraction occurs, let's say the image formed at this side. So this will be the V, position of image distance. So V positive or negative, since the image form same side with the object, so the image will be virtual and negative. What about R? Look at this position. If point C situated in a less dense medium, so R will be negative. Okay, so try to understand this sign convention table and we can apply it into the next example.